In this video I'm going to talk about centripetal acceleration. And this comes under the topic of circular motion. As I mentioned before in a previous video, when something is moving in a circle like this, circle of radius r, here's the object with a speed, or at this point has a velocity vector v. When it's moved round to here, its velocity vector has changed direction. It's the same magnitude, but it's changed direction. And since in circular motion velocity is always changing, there must be an acceleration. Let's draw our circle again. Here we go, here's the radius. Particle started out here at P and it ended up here at Q. And the angle that had been subtended was delta theta. Started off with this velocity vector Vp and it ended up with a velocity vector like this Vq. So the change in velocity vector is if we shift Vq over here, it's going to be this vector here. And from trigonometry it follows that this angle here is also delta theta. Just make that a bit clearer. Let's have a look a bit more in detail at this drawing here. So here I've got Vp, it's a vector. Here I've got Vq, and this is my delta V, and here is delta theta. Well, if I forget the directions for a moment, these velocities, then I could replace Vp and Vq with just V, the speed, the linear speed that the particle's going. And I can make this into a little circle sector of radius v and angle delta theta. That will give me this arc length of v delta theta. And we were wanting to find what delta v was. Well, when delta theta is small, we can roughly write delta v is approximately equal to the length of the arc v delta theta. And we're wanting to find the acceleration, not the velocity. We then have to find the change in velocity over the change in time. Well, we already have an expression here for the change in velocity, v delta theta over delta t. Well, the change in angle over the change in time, that was the definition for the angular speed. So the acceleration, angular acceleration, is just v omega. That's one expression for the centripetal acceleration. But we also know that omega equals the linear speed over the divided by the radius, which gives us another expression for the centripetal acceleration. That is a equals v squared over r. So, and this is an important result to note, that the centripetal acceleration is proportional to the square of the linear speed and inversely proportional to the radius of the circle. What about the direction of acceleration? Well, if we make, when delta t gets very small, then let's just magnify. Here we had the vector vp, here is vector vq, and here's the change in velocity. Well, as this angle gets very small, then we can approximate this angle to be a right angle. So the change in velocity, which is directly proportional to the acceleration, becomes normal to the initial velocity. So at any point on our circle where we have a velocity vector in red here, which is always changing, then the acceleration will be directed normal to that vector and pointing directly at the center of the circle. That's why it's called a centripetal acceleration. Let's Let's derive some alternate expressions for the acceleration finally. So if we start out from a equals v squared over r, then the first way we could rewrite this expression is by using v equals 2 pi r over t. This is the distance travelled in one cycle over the time taken to complete one cycle. So we get a equals 2 pi r all squared over t all squared all over r, which becomes 4 pi squared r squared t squared r. One of those r's cancels with that, and we end up with a equals 4 pi r over t squared. Another rewrite is using the relationship between linear speed and angular speed, which is v equals r omega. Putting that into the expression a equals v squared over r gives us a equals r omega all squared over r, which gives us r squared omega squared over r. One of those r's cancels with that one, and we get a equals omega squared r. There's also a final one, and that's that's just replacing the period here with 1 upon the frequency. We get, so substitute t with 1 upon f, we get a equals 4 pi r over 1 upon f all squared, which is the same as 4 pi r f squared. And that's the end of this video. Thank you very much.